Dear viewers, in this lecture, let us derive the Euler's crippling load for columns with one end fixed and other end hinged. So here it is fixed and here it is hinged. P is the critical load, and since this is a hinged support, there will be a horizontal load H. This is L. We consider a section XX at X distance from the fixed end. The deflection at XX is Y as usual. Now we are going to take bending mode at XX, that is bending mode at this point. So if you see to the left side, you'll be having this load P as well this horizontal load H. This P will cause a moment of P into Y. So anti-clockwise, therefore minus P into Y. This H will cause a clockwise moment. So H into this distance, there is a distance between the line of action of H and this point. So this will be, this is L, this is X, therefore this will be L minus X. So H into L minus X. We have EI d squared by dx squared equal to mxx. So this will be minus py plus h into L minus x. This shall be written as h into L minus x minus p into y. So bringing this py this side, EI d squared by dx squared plus py equal to h into L minus x. Dividing this equation throughout by EI, will be getting d squared by dx squared plus p by EI into y equal to h by EI into L minus x. The solution for this differential equation will be y equal to, as usual, write a cos x root p by EI plus b sin x root p by EI. And there will be some additional term. This additional term we can remember like this. If we have h into L minus x, this p will come here. Therefore, h into L minus x by p will be the additional term. This is equation 1. Now we need to find the constants a, b using the boundary conditions. So if you see the boundary condition, at a fixed support, slope is 0 as well, deflection is 0. At hinged end, only deflection is 0. So these can be written in the form of boundary conditions as when x comes here, x equal to 0. So when x equal to 0, y equal to 0. Similarly, when x comes here, when x equal to 0, the slope dy by dx is 0. So these are the two boundary conditions for this n. And for this n, x equal to L. So because x will take a value of L, at x equal to L, y equal to 0. So these are the three boundary conditions. We need to substitute and get the values of the constants. So using the boundary condition 1, that is put x equal to 0 and y equal to 0. So 0 equal to a cos 0. Therefore, a plus this will get cancelled plus h into L minus x by p, put x equal to 0, hl by p. So you will be getting a plus hl by p. Therefore, capital A equal to minus hl by p. Then we need to differentiate this equation before applying the second boundary condition. So if you differentiate this, dy by dx equal to a cos x root p by a will become minus sin x root p by ei multiplied by, we need to differentiate this with respect to x. Therefore, if you differentiate this with respect to x, you will be getting root p by ei. And sin x root p by a will be cos x root p by ei multiplied by, differentiate this with respect to x, you will be getting root p by ei. Then if this is differentiated with respect to x, we will be getting minus h by p, because hl will get cancelled, minus hx by p. So minus h by p will be the differentiation. So we will be getting minus h by p like this. Minus a sin x root p by a into root p by ei plus b cos x root p by a into root p by a minus h by p. Now using the boundary condition 2, that is put dy by dx equal to 0 and sin 0, this term will get cancelled. This will become b cos 0 will be 1. So b into root p by ei minus h by p equal to 0. Okay? B into root p by a minus h by p equal to 0. So substituting and taking this side, you'll be getting b equal to h by p into root ei by p, because when it goes this side, you'll be getting this. Therefore, you'll be getting b equal to h by p into root ei by p. This is the correct term. So this is not correct, because here actually you should have b into root p by ei minus h equal to 0. This is not correct. So b into root p by ei minus h by p, p into root p by ei minus h by p equal to 0, from which we will be getting b equal to h by p into root ei by p. So substituting the value of b, you will be getting y equal to minus hl by p cos x root p by a plus h by p root ei by p sin x root p by ei, h by p root ei by p into sin x root p by a plus h into L minus x by p. Now using the third boundary condition, put x equal to L and y equal to 0. You're getting 0 equal to minus hl by p cos L root p by a plus h by p root ei by p into sin L root p by a plus this will get cancelled because L minus L will be cancelled. Therefore, you'll be getting minus hl by p cos L root p by a plus h by p root ei by p sin L root p by a equal to 0, from which you can write sin L root p by a divided by cos L root p by a equal to hl by p. This we have here, hl by p into, this will become P by H into root P by EI. Therefore, we'll be getting, this is, this will become tan L root P by A equal to L root P by EI. So this is possible only when L root P by EI is equal to 4.5 radians. And this is very small value. 4.5 radians means in terms of degree 4.5 into pi by 180. So if this is that value, then tan theta will be equal to theta. So this value should be equal to 4.5 radians. So squaring on both sides, you'll be getting L squared P by E equal to 4.5 squared will be 20.25. Therefore, P will be equal to 20.25 EI by L squared, and 20.25 shall be replaced by 2 pi squared, because for all the other end conditions we have in terms of pi squared, EA by L squared, pi squared A by 4L squared, 4 pi squared A by L squared. So everything in terms of pi squared, you will express this also in terms of pi squared. Therefore, this will be P equal to 2 pi squared EA by L squared. This is the Euler's crippling load or buckling load for the end condition, one end fixed and other end hinged. Thank you viewers for your patient listening, and thank you for subscribing our channel and making it reach many. Thank you.